The periodic table is a magnificent map of the building blocks of our universe. It arranges the elements not just by number, but by family. Each vertical column, or group, tells a story of shared character. Today, we journey down Group 5. Here we find 4 fascinating metals: vanadium, niobium, tantalum, and the elusive dubnium. These elements are not household names like iron or gold, yet they are the unsung heroes that power much of our modern technological world. From the strength of our tallest buildings to the tiny components inside our smartphones, their influence is profound and widespread. They are a family bound by chemistry, yet each member has its own distinct role to play in the grand cosmic drama. So what does it mean to be in Group 5? This shared configuration dictates how they interact with other elements, giving them a related set of chemical behaviors. They are all transition metals, known for their strength, high melting points, and ability to form colorful compounds. As we travel down the column, from the lighter vanadium to the much heavier tantalum and beyond, we see beautiful, predictable trends. Understanding this one column opens up a window into the elegant order that underpins all of matter. This essay will guide you through this remarkable group, one element at a time. We will explore their individual properties and the surprising ways they have been harnessed by science and industry. We will start with vanadium, the workhorse alloy. Then we move to niobium, the key to powerful superconductors. After that, we meet tantalum, the resilient metal inside our most personal electronics. Finally, we will touch upon dubnium, an element that exists only for fleeting moments in laboratories, pushing the boundaries of our knowledge. Our exploration begins with vanadium atomic number 23. This is a hard, silvery gray metal that feels surprisingly light for its strength. Vanadium is not an element that likes to be found alone. It is almost always bonded with other elements in one of over 60 different minerals. Its defining characteristic is its remarkable ability to impart strength. When you think of the toughest steel used for tools, axles, and building skeletons, you are often thinking of steel that has been fortified with just a tiny pinch of vanadium. It is a classic example of how a small addition can create a massive improvement, transforming a simple metal into a high-performance material capable of withstanding immense stress and wear. The primary use of vanadium, accounting for the vast majority of its consumption, is in the creation of steel alloys. Adding as little as 0.15% vanadium to steel can double its strength. This alloy, known as ferrovanadium, is the backbone of heavy-duty machinery, high-pressure pipelines, and the reinforcing bars that give skyscrapers their resilience. Vanadium compounds, particularly vanadium pentoxide, are crucial catalysts. They speed up chemical reactions without being consumed, most famously in the production of sulfuric acid, one of the world's most important industrial chemicals. A new and exciting frontier for vanadium is in energy storage through vanadium redox flow batteries, which promise large-scale, long-lasting power storage for our energy grids. Vanadium is not particularly rare, being more abundant in the Earth's crust than copper or zinc. It is extracted from various minerals, recovered from steel-making slag, and from certain crude oils. Isolation uses high-temperature reductions, often with calcium or aluminum. Major global producers include China, Russia, and South Africa, making its supply chain geopolitically important. Solid vanadium is stable, but fine dust and oxides can be toxic. Workers rely on protection and ventilation. Journeying further down Group 5, we encounter niobium atomic number 41. Often found alongside its heavier sibling, tantalum, niobium is a lustrous, gray metal, soft and ductile when pure. Niobium's most celebrated property is its talent for superconductivity. At extremely cold temperatures, just a few degrees above absolute zero, alloys of niobium lose all electrical resistance. This allows them to carry powerful electrical currents with zero energy loss, enabling advanced medical and scientific instruments. Niobium titanium and niobium tin alloys power superconducting magnets for MRI and particle accelerators. These magnets guide subatomic particles on near-light-speed journeys. Beyond this, niobium microalloys strengthen steel, adding toughness and weldability for bridges, cars, and pipelines. It holds strength at very high temperatures in jet engines and rocket nozzles. Sourced mainly from pyrochlore and columbite, especially in Brazil and Canada. Biocompatible and hypoallergenic, niobium is safe as metal. Powders need ventilation. Our next stop in Group 5 is tantalum, atomic number 73. It is a heavy, dense, blue-gray metal, exceptionally hard, with one of the highest melting points. Named for Tantalus, early chemists were endlessly frustrated trying to isolate it. Tantalum's defining feature is its incredible resistance to corrosion, nearly immune to most acids below 150 degrees Celsius, as resilient as platinum but far cheaper. The most widespread use is in electronics. It's ideal for miniature, high-performance capacitors. A tantalum capacitor stores significant charge in a tiny volume. Smartphones, laptops, digital cameras. Its inertness makes it excellent for implants, artificial joints, bone plates, cranial meshes. It does not corrode or trigger immune reactions. Tantalum is extracted from tantalite, often mixed with niobium's columbite, the combined ore called coltan. Coltan mining has major ethical controversy, especially in the DRC, linked to conflict and human rights abuses, driving responsible sourcing and recycling. Separation from niobium is chemically challenging but essential for high-purity tantalum. Key producers include Australia and Brazil. The main concerns are origins, not chemistry. Ethical supply chains and improved recycling are critical. As devices shrink and performance climbs, tantalum demand meets the engineering and ethical challenge of sustainable tech. Section 5. Dubnium, DB. The fleeting laboratory marvel. The final and most mysterious member is dubnium, atomic number 105. Unlike its relatives, you will never find dubnium in the Earth's crust or in any device. It is a synthetic element, created only in particle accelerators. Dubnium is a transuranic element, where nuclear forces are pushed to the limit. Its existence is incredibly brief. The most stable isotope lasts just over a day. Most vanish in seconds or less. Because of that instability and rarity, dubnium has no practical applications. Its value is purely scientific. Physicists smash lighter nuclei like nitrogen or neon into heavier targets such as californium or americium. Very rarely they fuse to form dubnium. The resulting atoms are identified before they decay. Only a few atoms form at a time. Labs use extensive shielding and remote handling. First synthesized in the late 1960s at Dubna in Russia and also at Lawrence Berkeley Laboratory. Each isotope advances nuclear theory, stepping toward the predicted island of stability, pushing into the unknown, one atom at a time. For everyone else, dubnium poses no threat whatsoever, an elemental ghost that exists only to expand knowledge. When we step back and look at vanadium, niobium, and tantalum as a collective, a clear family resemblance emerges. They are all strong, hard, refractory metals, highly resistant to heat and wear. Vanadium melts at 1,910 degrees Celsius. Niobium at 2,477. Tantalum at 3,017. This durability comes from strong metallic bonds, hence their value in alloys and high-temperature uses. 5 valence electrons guide their chemistry, enabling multiple oxidation states. The +5 state grows more stable down the group, yielding key oxides V2O5, Nb2O5, and Ta2O5. Niobium and tantalum are almost always found together, requiring sophisticated separations. They form stable carbides and nitrides, extremely hard ceramics for tools and protective coatings. Even in small quantities, they impart strength and resilience to steels, economically vital. In pure form, VNB and Ta share a silvery luster. Dubnium likely would too, reflecting deeper unity. They are a family by position and by purpose, strong, resilient, and profoundly useful. Despite their family ties, differences emerge down the column as size and mass increase. Density rises, vanadium about 6.1, niobium 8.6, tantalum 16.7 grams per cubic centimeter, over twice steel. V and NB excel in strong, lightweight aerospace alloys. Ta's heft is fine in miniature electronics. Reactivity shifts. Vanadium is most reactive of the trio, niobium more resistant, and tantalum stands in a class of its own. Tantalum's extreme inertness makes it ideal for corrosive chemicals and inside the human body. Vanadium strengthens steel. Niobium enables superconductors. Tantalum rules capacitors with reliable high capacitance per volume. These roles are not interchangeable. No MRI from vanadium, no top-tier phone capacitor from niobium. V, NB, and Ta are stable, mined, and indispensable. Dubnium is radioactive and momentary, a cousin known through theory and experiment. Their journey spans geology, chemistry, and engineering, from Earth's crust to our hands. As solid metals, V, NB, and Ta are generally safe. Hazards arise mainly from powders and vanadium compounds, managed via ventilation and PPE. For users, vanadium hides in tools and structures, niobium in infrastructure and science, and tantalum in the devices closest to us. The Group 5 elements offer a perfect snapshot of how the periodic table works, a shared atomic architecture that yields strong, high melting point metals. This heritage explains why vanadium, niobium, and tantalum excel as alloying agents, yet each has a unique specialty. Subtle shifts in density, reactivity, and electronic structure down the column lead to vastly different roles. Vanadium is the affordable bulk strengthener for steel. Niobium unlocks advanced medical imaging and fundamental physics. Tantalum's corrosion resistance and electrical properties make it the quiet heart of our digital lives. And dubnium pushes knowledge to the frontier. They are not interchangeable. Each excels in its niche. Rarity and concentrated supply remind us, ethical sourcing and robust recycling are essential for a sustainable technological future. Group 5 is a testament to human ingenuity, finding, understanding, and harnessing elements to build a stronger, more connected world. From vanadium steel to niobium superconductors to tantalum electronics, quiet enablers drawn from the magnificent order of the periodic table.